Okay, let's talk about the scientific revolution. First, what was it? Basically, it was a giant transformation in the way that European intellectuals saw their world. And at its heart, it was a battle between the traditional medieval Christian worldview, as portrayed in the Bible, and a new scientific worldview. There's a picture of Galileo, the astronomer, facing down the church, very romantic picture, obviously painted years later. This is from 1857. But it sort of captures this idea of science facing down theology, facing down this medieval worldview, which these sorts of fights go way back. You know, the Greeks had them. Do you believe the gods, or do you believe guys like Plato or Aristotle? So this was a new conflict between these different ways of viewing the world. Now, there's a lot of different people involved in this science revolution, but one of the men at the heart of it is this man, Sir Francis Bacon, Englishman, 1561 to 1625. His big book in 1620, New Directions, Novum Organum, basically outlined a way of looking at the world. It didn't discover anything particular itself, but it said we need to examine the world basically with new eyes. And he came up with the idea of what we now call the scientific method, particularly focused on using experiments. Don't just come up with theories, come up with some way of proving your theory. And this was an incredibly revolutionary concept, and people built on Bacon's idea of using experiments to explain the world. Bacon himself was wrong about all sorts of things, by the way. He didn't always come up with the right answers, but his basic method was revolutionary. Now, this new way of looking at the world, first off, it's developing before Bacon. Bacon doesn't start this. He sort of just explains some of the stuff that's going on. And it's the stuff that we're calling science was in all sorts of areas. Down here we have Andreas Vesalius, who was a physician and essentially biologist. He came up with a book on the fabric of the human body, which revolutionized people's understanding of human anatomy. Basically, up until then, doctors who weren't very good, and by the way, weren't very good after then either, but maybe a little bit better, had some confused ideas about how exactly the body worked. Vesalius had a really kind of crazy idea to figure it out. He said, let's look at the body. And so he chopped up corpses, cut them open, and saw how they functioned. This, by the way, has been very controversial for centuries because there is something seen as like almost satanic. It was evil. It was wrong. And so doctors, medical men who wanted to study the human body often had to hire sort of skeevy individuals to acquire bodies for them to cut open and figure out how they worked. But gradually, people began to get an actual idea of how the actual human body works, where the muscles are, where the bones are, all those exciting things. William Gilbert here experimented with magnetism and electricity. In the picture down below, he is showing, this is a later painting, but he is showing Queen Elizabeth how magnetism works. And he actually coined the word electricus, which later on is turned to electricity. So an early experimenter in that area. But the key area where the scientific revolution is, focused on, or maybe a better way to put it is the key conflict of this era was on the question of how exactly did the solar system work? What was at the center, the Earth or the Sun? The classic view, and this dates back to a guy named Ptolemy in the 2nd century Common Era, and is also the Church's view, is that the Earth is the center. There we get a picture from Ptolemy's work showing the Earth there at the center, and around it are the various Mercury, Venus, the Sun, Mars, Jupiter, all in various orbits going around it. The idea was that there were a bunch of spheres, like a giant glass balls around the Earth, and they would move in various directions, and the planets and the sun were in those spheres. So there's a sort of easier to see picture on the lower left side. You can see the Earth at the center and all the various planets and the sun going around it, which was incredibly egotistical, if you think about it. everything goes around the earth. Everything goes around us. Remarkably full of themselves, these earthlings. So, as far as the church was concerned, this was the truth. And anything that went against this was against the Bible, was against the church, it was against God. It was heresy. So this guy here is going to cause problems. Nicolaus Copernicus. Copernicus comes up with a heliocentric view of the universe, saying everything goes around the sun, not the earth. Because the problem that Copernicus and others had is if you look at the sky, the sun's fine because it looks like the sun's going around the earth. The moon, okay, actually does go around the earth, but the other planets don't. And if you look at how they don't move in nice circles. They move kind of in jaggy lines because, well, they're not really going around the earth. And people came up with elaborate theories about why this was, but Copernicus said, what if it's all wrong? What if really everything goes around the sun? It will make everything make a lot more sense. Now, it's easy to make fun of these people for not seeing what Copernicus saw. By the way, he publishes his book the year of his death. He's like on his deathbed, and he publishes the book because he doesn't want to get in trouble. He's going against the church. He's going against the Bible, or at least people's interpretation of the Bible. But before again, we make fun of these people for getting the science wrong, think common sense. There's the Earth. It's about 24,000 miles around. Now, people knew the Earth was round. Remember, they knew that. So they knew it was about 24,000 miles around. So according to Copernicus's crazy theory, the sun doesn't go around the Earth. Instead, the Earth spins and makes it look like the sun is going around the Earth. All right, so the Earth spins. How often does the Earth spin? Think about that for a second. How long does it take the Earth to go those 24,000 miles? And okay, the answer is, of course, 1 day. It takes 1 day to go 24,000 miles because the Earth spins around in 1 day and then it's a new day. All right, how many hours? 24 hours. So 24 hours in a day, it spins 24,000 miles in 1 day. So how fast is it going? Do the math. How fast is the Earth going if it takes 24 hours to go 24,000 miles? Did you do it? All right, I'll give it to you. 1,000 miles an hour. 1,000 miles an hour, 24 hours, 24,000 miles. So the Earth is spinning 1,000 miles an hour. After you watch this exciting video, go outside and ask yourself, does it feel like I'm going 1,000 miles an hour? If you were really going 1,000 miles an hour, wouldn't you be falling over? Wouldn't all the cars and the cats and the dogs and the people all be flying by, washed away by a giant wind? It's obvious we're not going 1,000 miles an hour. It's nonsense. Except, of course, we really are. Common sense is wrong, and we really are. The thing people couldn't wrap their brains around is everything's going 1,000 miles an hour. When you walk outside, yeah, you're going 1,000 miles an hour, and so's the air, so are the trees, and so it's sort of like being in a car. And if you drop something in the car, like you drop a ball in the car, it's not going to go flying past you because everything in the car is going 60 miles an hour. So when you drop the ball, it's going forward at 60 miles an hour, just like the car. And so in the car, it looks like it's not going forward at all. Make sense? But if you drop that ball out the window, suddenly it would be gone. I don't know why you're dropping the ball out car windows, but that's your choice. So this 1,000 miles an hour thing, at first hand, doesn't make sense. I'm just saying we can understand why these medieval thinkers had a hard time wrapping their brain around Copernicus's new idea. Except he's right and they're wrong. Now, by the way, you're not really going 1,000 miles an hour. I don't want to lie to my students. So what do I mean? Well, see, why do I mean you're not going 1,000 miles an hour? Put it this way. If you're in New York City, you're not going 1,000 miles an hour. If you're in Colombia, you're going about 1,000 miles an hour. But New York City, why not? Because the Earth, well, I'll show you an image. There you go. So if you're at the equator, you're going 1,000 miles an hour. If you're at New York, you're probably going about 730, 750 miles an hour. If you were at the North Pole, you'd be going 0 miles an hour. Think about it. A ball spins. The outside part of the ball is going all the way around. It takes it a while. But if you just put your finger at the top, that part's barely spinning at all. In fact, if you were standing at the North Pole and waiting for you, it would take you a whole day to spin around, even though you'd be spinning around like, wherever your feet were, like a 2-foot gap. So it would be incredibly slow. So it depends where you are on the planet Earth, how fast you're going. But at the equator, yeah, you're going about 1,000 miles an hour. Crazy idea, but true. All right. If Copernicus came up with the idea, Galileo Galilei basically popularized it. He read about it, he heard about it, he thought, this makes sense to me. And even more importantly than thinking it made sense to him, he did what Sir Francis Bacon suggested people should do, is he examined it. He basically did visual experiments. He developed his own telescope. He'd heard about a different kind of telescope, so he made his own. And then he used the telescope to look at the sky and see things in the sky that matched the sun-centered solar system. For example, he could see holes in the moon, craters in the moon, which suggested that there were things flying through space, banging into the moon, which meant not everything was going neatly just around the Earth. There were things like randomly flying through the sky, which of course is true. He could look at Jupiter, and he could see there are moons going around Jupiter. Once again, showing not everything goes around the Earth, because now he can see moons going around something else, going around Jupiter. So these things convinced him that Copernicus was right and the medieval view was wrong. However, the church was not ready to accept this. This was an attack on their doctrine, on their beliefs. And so he was forced by the church to back down. And in 1633, he was forced to recant. He was forced to say all the stuff I said before wasn't true. And he was put under house arrest for the rest of his life, because the alternative was basically, being tortured or burned to death, and he didn't want that, so he backed down. His books were ordered banned, but of course there were copies everywhere, and people made copies. And one of the things to think about is this is the Catholic Church saying in 1633 you should not read Galileo's books. Not everyone's a Catholic. Telling Protestants elsewhere in Europe not to read a book because the Pope says it's bad. Think how much Protestants didn't like the Pope. So if the Pope says a book is bad, Protestants are going to buy extra copies, give them to all their friends. So Galileo's words were not actually banned. I mean, the Pope tried to ban them, but they spread everywhere. And other people could look at the sky through telescopes, and they could see what Galileo saw and see that he was right. So this attempt to ban his ideas was obviously not successful. It was hard on him personally, but the ideas kept on spreading. Which brings us to this guy, Isaac Newton. He is born the year Galileo dies, and he is basically sort of the man who represents the victory of the scientific worldview. His big book is in 1687, and he publishes the Principia Mathematica, which lays out his idea of, well, basically, it explains why things do what they do. Copernicus came up with a theory of stuff going around the sun, and Galileo looked through his telescope and said, yeah, that's what I see. But Isaac Newton came up with a theory for why it happens. Now, I know you guys have heard the whole Isaac Newton invents gravity, or some garbled version of that. And of course, Isaac Newton did not invent gravity. People knew things fell down. What he did was come up with a theory of gravity, a theory for how gravity worked. And you find this in his Principia Mathematica. He also developed a mathematics to explain things. He basically invented calculus. That's a little controversial, by the way. There was another German mathematician named Leibniz who also invented calculus, and they argued for years over who invented it first. And the general consensus is they actually both invented their own version of the calculus at about the same time. But in any case, Isaac Newton was a pretty smart guy to invent calculus. I barely passed calculus, so I'm impressed. So he doesn't invent the idea of gravity, but what he does is explain gravity. And I'm sure you've heard the story of supposedly he was sitting in a garden and an apple fell on his head, and he was like, oh my gosh, things fall down. Okay, he knew things fell down. That story is pretty clearly apocryphal, a false story. But the better story, which I think is probably also not true but makes more sense, is Isaac Newton is sitting in a garden and he's looking at an apple tree and he says, okay, the apple's going to fall down, but the moon up in the sky isn't going to fall down. Why is the apple going to fall down and the moon not going to fall down? And so this is sort of the thought experiment which leads to his larger mathematical explanation. And there are basically two parts to it. The first part is gravity, which you see in that little diagram on the, well, the one right here with the purple and the yellow. Basically what it says is gravity is a formula which you get from taking the mass of object 1, m1, times the mass of object 2, m2, divided by the distance squared. So the bigger the things are, the more gravity there is between them. But the farther apart they are, the less gravity. And he gave that a mathematical formula. m1 times m2 over r squared. That's part one. Part two is he comes up with his laws of motion. There are 3 laws of motion. And the one we're concerned with is the first law: an object in motion tends to stay in motion, an object at rest tends to stay at rest. So once something starts to go, it just keeps on going unless something stops it. So how does this explain the moon? Well, basically for some reason, and Isaac Newton didn't know why, but he said for some reason, the moon is going forward. So it's an object in motion. It's going to keep on going forward unless something stops it. Well, there's gravity. Now, gravity doesn't stop it. Gravity pulls at it. And so what happens is there's clearly a balance between the moon going forward and gravity pulling it down. So instead of flying off into space or crashing to the Earth, it's balanced between those two things, and so it just keeps going around the Earth. And he came up with the math to describe how that happened. And of course, that same math also describes how the Earth goes around the sun, how Mars goes around the sun, how the moons of Jupiter go around Jupiter, all of them described with Newton's laws of motion, his theory of gravity, and using calculus. And the neat thing about Isaac Newton is you take all the stuff that he figured out and you plug the solar system into his theories and it comes out. The math adds up. Newton's theories explained how the solar system worked. And that's what makes him such an incredible guy. By the way, he was also, supposedly from his own time, more than a bit of a jerk. Very jealous, petty, not the nicest human being in the world, but very, very smart. So with Isaac Newton, we basically have the victory of this scientific worldview, because Isaac Newton's ideas show that he could mathematically describe the solar system. This doesn't mean that the church and science haven't continued to be in conflict, because of course they have continued from then until now. But it was a kind of victory for this new worldview. And people are going to build on it to develop a new, more complicated technological civilization in Europe. Okay, that's it for science for now, and we will talk later.